back with people in the room. Hopefully also many of you online. Today's speaker is Daniele Marinazzo, who's a full professor at the Department of Data Analysis at the University of Ghent in Belgium. And just a brief historical background. So Daniele did a master's in physics from 1995 until 2001, as well as a PhD in physics from 2003 until 2007, both at the University of Bari in Italy. Then he had a postdoctoral stint at the CNRS, University Paris Descartes in France. And then he actually moved to where he is today in 2011 to the Department of Data Analysis at Ghent, where he was first an associate professor, then promoted to associate professor in 2016, and to full professor by a fast-track competitive procedure in 2020. By his background, Daniele is a statistical physicist who's focusing on methodological and computational aspects of neuroscience research, and on dynamical networks subserving function. His group develops new techniques for inferring connectivity architectures from the dynamics of the recorded neuroimaging data. And in this venture, they have produced, and you have produced, far more than 100 publications on very diverse aspects of the quantification of neural network interactions. In particular, Daniele has made substantial contributions to inferring causality from functional interactions using approaches such as Granger causality. Moreover, he and his colleagues have championed the characterization of higher order interactions in neural data, something that we will hear about in a second. Daniele is also very active in the community support and the multidisciplinary mentoring of the next generation of network neuroscientists. He's a deputy editor at PLOS Computational Biology and co-editor in chief at Neurons, Behavior, Data Analysis and Theory, as well as academic editor at several more journals. He's also representative of Ghent University in eBrains. Today's presentation is called Higher Order, I think higher order in brackets, Higher Order Informational Interactions, Ideas, Implementations and Applications in Neurosciences and Behavioral Sciences. And we very much look forward to your presentation, Daniele. Thank you very much for coming.
Thanks. Okay. I'm not so proud of having a 4-line title, but again. Anyway, so when we, thanks, by the way, for being here. This thing work? No, never mind. I'll use this one. So when, no, or maybe yes, yeah, no, it should work. Good. So when we study the brain, so this is an example for large-scale brain activity, but of course, this can be generalized to other scales, as we will see later. We have different variables. We have the structure, we have the recorded activity, and then we have some statistical patterns that we observe, at least when we embark into connectivity. We will see this in a moment. Then we also have local measures, which sometimes are even more telling than connectivity itself. But depending on what we want to do, we might embark in the study of these statistical patterns. The idea is that, anyway, the ultimate goal is to see how the brain works. And one of the major characteristics of the brain is to integrate information across different areas in a synergistic way. So let's say that the concept of synergy, before being operationalized in one of the possible ways that we will see in a moment, is already a target property. Because another thing, a relevant thing when we study functional connectivity, is that sometimes we confuse the map with the territory, and so we have our target properties, so the interaction between brain areas and so, and then we have the measures that we use to quantify this. And sometimes in this match or mismatch between the target properties and the methods, we get lost. Anyway, here we have synergy as a target property, then we will see synergy as a method to infer something about this synergy. So this interaction happens at multiple temporal and spatial scales. So here we see some typical example from seminal books such as the one by Olaf Sporns and some other reviews. So from molecules to the whole network system and also social networks, this is a spatial scale, and the temporal scale go from a millionth of a second to human lifetime and beyond. Just since we mentioned Olaf and colleagues, we can take as a paradigmatic example of this quest Edelman's lab of a few years ago with two eminent scholars and pupils of Edelman, so Olaf Sporns and Giulio Tononi, which developed some ideas along this line. Basically, the idea is that it's good to have integration and it's good to have segregation. So segregation, different brain areas doing different things, and then integration of these functions. And so indeed, they must coexist. And so Giulio brought this to his theory of consciousness, and Olaf to the network neuroscience field, let's say. And by the way, it's good that even if we were using this kind of slides even before that, then Olaf in the review a few months ago eventually put the information also into the framework, which I'm glad he embraced. But we joke with him about this, but I'm happy that we got there before Olaf. Anyway, so the idea is to make sense of differentiation and integration. And what I will say today is that information is indeed a convenient way of doing so. What I was saying before about the target properties and the methods. So if we look at the occurrence of words containing connectivity, network, connectome in the OHBM abstracts, we'll see a kind of explosion, which now somehow subsided, but at least taking over almost half of the abstract, and cumulatively more than that. Of course, there is also some redundancy between these things, so they can sum up to more than 100 anyway. And then also functional connectivity, of course, it grows. This is already normalized graph, so it already takes into account the fact that we are publishing more and more. And again, we made up the name functional connectivity for statistical dependencies for some reason. When we talk about networks, we can think about at least two key characteristics. One is network as pathways, so the well-known problem of the 7 bridges of Königsberg, which has been told to have given rise to network science, in which a network was seen as a pathway, even if sometimes some colleagues think about pathway even when the network is inferred from statistical dependencies, and this is a bit problematic. Anyway, this is Königsberg today with an extra bridge, so graph theory would not have been born today. And then the second key characteristic of a network is an expression of collective dynamics, so it's a more wide sense, a more wide definition. For example, when we talk about intrinsic networks of the brain or network of people, so we don't necessarily think about the individual links, but in general of groups of individual or groups of part making things together. And then this concept has been present since quite a while. So started even from social sciences. So there was Adolphe Quetelet, which by the way was from Ghent, who was a kind of big data scientist ante litteram, because he was kind of obsessed with characterizing the average man, so the homme moyen, as he named it. So he came up with a body mass index and also some theories about the criminal behavior. And so in his ideas, basically every behavior, even a criminal one was somehow a statistical deviation around an average behavior, which was dictated by the society. So this was some argument in the debate of free will. And then it's been told, even though it's not a fact, that his theory could have inspired Boltzmann in his gas theory. And then, anyway, similar concept resonated also in the theory of neurons, and in particular, the Nobel Prize shared by Camillo Golgi and Santiago Ramón y Cajal, which basically came from two complementary positions, segregation and integration. So Golgi was more about the integration part, and Cajal more about the segregation part, if you want. Anyway, if we think about network to conceptualize this concept, there are some limits in pairwise network representation. So some limits are, let's say, statistical. So, for example, the presence of confounders and colliders, which are quite known in some fields, much less so in neuroscience. So when we talk about network of statistical dependencies and we build a pairwise network, we could have some problems in defining the networks, but also once we have the networks, to define some network properties on networks built by full adjacency matrix, in particular with this conceptual confounders. And then we have some more fundamental also limitations. So even a simple unit such as the XOR gate is problematic to represent as a pairwise network, because we cannot tell basically what happens here if we don't know both of these two things at the same time. And also key figures in the machine learning and artificial intelligence somehow see as serendipitous the concept of statistical synergy in this sense. So the network community already came up with some extensions to pairwise graphs, which is hypergraphs and higher order interactions. So we have different constructs such as simplicial complexes or hypergraphs, in which networks are considered as not only in their pairwise interaction, but also in groups. So for example, one clear representation of a hypergraph is in epidemiology. So for example, if now there is a virus in this room, it does make really a lot of sense saying that there is a link between me and Stefano, me and Klaus, me and Kaysen, etc. So, but it's more as an hypergraph which share in this case some a virus, or if you want, some knowledge, hopefully. Now the thing is that how do we go from to this representation from the statistical dependencies? So we can have some mechanism that give rise to higher order interactions. So for example, in this paper, which tackles the problem from the generative point of view of models in physics, they have again different constructs like a network, hypergraph, and simplicial concepts and complex, and then they have some higher order mechanism. So for example, here is a Kuramoto-like model, which has some links which are beyond the pairwise links. So we have 3 or 4 nodes being together linked, and they see that, for example, some aspects such as explosive synchronization so happen in presence of this higher order mechanism. On the other hand, one thing is a mechanism, and one other thing is what we observe. So we have the level of so if you think about the brain, we have the level of neurons and their interaction. Then we have the level of what we observe, so our measurements and our functional connectivity measures. And then we have a third level, which is the level of inference. that brings us back to our target properties from our observations. So if we only look at the dynamic of a system and we want to infer something about not only the mechanism, but about the behavior of the system, we should somehow decouple from the mechanism itself. So, for example, there are some papers which, for example, they try to predict the dynamics of a network without the knowledge of the interaction graph. And this is, of course, a nice result, but it's definitely not surprising if we think that we can model a multivariate system, which can be the expression of several generative models, and then be able to predict its future. So in this case, we don't need necessarily to know how the time series have been generated. And so, as a correspondence to the previous paper, we propose to disentangle the mechanism from the behaviors, again in complex systems, but it's something that can be generalized to all the systems that we study. So to separate these two points of view, we can look at higher order mechanisms, which are more rather structures and interactions, and higher order behaviors, which are, on the other hand, the statistical properties and observable behaviors. So the former speaks to how the system is structured, and the latter is more aimed at what the system actually does. And so, for example, some early efforts of looking at the hypergraphs of functional networks, basically, they took the pairwise functional connectivity, even the seminal paper by Rolf Kotter, I don't know if also Klaus was in there, on the cliques and motifs in functional structural network. They took a pairwise interaction and then find the triplets or the quadruplets, so which, let's say, is a bit problematic in the sense that when you have a network of full adjacency matrix, then it's not completely principle to detect higher order interactions when you don't have something which is a clear pathway as with the cause associated, etc. So an alternative approach can be to infer these higher order quantities rather directly from the data. So this is a simple case of the ISING model, in which you have the mechanism, which is basically we can have individual or 3 ways or 4 ways interactions in the Hamiltonian, and then the observed behavior can be also pairwise or multivariate. And for example, notably in the case of a frustrated spin system, we see that the most of information is found when we consider the interaction of the 3 spins as a whole rather than the individual pairs. Another case in neuroscience where a higher order effect can make a difference comes from these 2 studies. So a first study which showed that indeed a null model made of a pairwise correlation was enough to describe the complexity of the data, but then a subsequent paper showed that this is true when the retina is exposed to white noise stimuli. On the other hand, when the retina is exposed to a natural image, let's say even a model which randomizes up to the second order correlation still doesn't completely fit the data, so higher order interactions are necessary. And so basically the idea is to operationalize the concept of synergy and redundancy to make sense of these higher order interactions. And by the way, even if you interrogate some artificial intelligence about the concept of synergy redundancy, you have this kind of linear geometry for the redundancy, this kind of circular for the synergy. So the idea to look at synergy and redundancy from the information point of view comes to collect information and see whether you have some extra information that comes from different parts of the system, in particular information that tells you more than the individual contribution. So in this case, for example, there's two witnesses of a specific crime and talking about the suspect. So there is some unique information, some redundant information, and then some synergistic information, which leads eventually to increase our knowledge. And this is it can be operationalized by means of a multivariate probability distribution. And so if we define information as the amount by which one variable in a wide sense, which can be the answer to a question, some measurement, etc., reduce our uncertainty or surprises us about another variable, or actually even about itself. This is basically the definition of entropy, which has been quantified by Shannon using logarithms and probability distribution. And then when we go to pairs of variables, we can define other quantities, such as, so we have the two individual entropies, then we have the conditional entropies, we have the joint entropy, which is this one, and then we have the mutual information. So for example, we know that the joint entropy of a system is equal to the two individual entropies only when the two variables are independent, and so only when the mutual information is equal to 0. On the other hand, when two variables share some information, the joint entropy is no longer the sum of the two individual entropies, and indeed we can define the mutual information as either the sum of the two individual entropies minus the total entropy, or one of the two minus its conditioned version, and this is a symmetric quantity. We can extend this to 3 variables with the interaction information. So now we have 3 variables. And in this case, the interaction information is again a symmetric quantity, so it's invariant under permutation. And in particular, by looking at the intersection between the different mutual informations, we can see whether the interaction information of the system is greater than 0 or smaller than 0. And this was one of the first definition of higher order informational interactions, in particular of synergy and redundancy. So synergy when there is no overlap between the pairwise mutual information with respect to a third variable. In this case, it's called S because it is denoted as an external stimulus. So in this case was maybe 2 neurons responding to a third to a stimulus as a third variable, or redundancy when there is overlap between these two. And there are some relevant examples in neuroscience. So for example, indeed, information coded by neurons. So some neurons can code information which can be synergistic or redundant, depending on whether they code similar things or the two things are different and they add information, or it can be independent. Or in signal processing, you have examples such as the Markov chain, with so in case of unidirectional Markov chain, the interaction information is greater or equal than 0. On the other hand, it's strictly greater than 0 when you have a bifurcation in the information. Sorry, I just have to take off my microphone. Sorry. Okay, hope you still hear me. And then another relevant example is the data processing inequality, by which if we have Z as the processed version of Y, you see that the mutual information between X and Z is smaller or equal than the minimum between the mutual information between X and Y and Y and Z. So basically, a processing cannot increase information. So to make sense of synergistic effects, we can operationalize the concept of synergy, and we have two main information-based strategy. One is the interaction information decomposition, which is the one that I just introduced, and then another one that we will see at the end of the talk, which is the partial information decomposition, which allows synergy and redundancy to be both present at the same time as distinct non-negative quantities. Of course, we talk about pairwise and triplets, but of course, we can and we should probably go beyond triplets. Then, of course, there are different strategies, more or less complicated or not. So one of the first implementation was by Stefano, among others, in this paper. And then other study, for example, the study by Bettencourt, which used mutual information expansion as a Taylor series. So every time that you found a zero term, so you have independence and the expansion stops, and this was extended to transfer entropy by simply introducing a conditioning operator, which conveniently commutes with the Taylor series-like operator here. On the other hand, this was still computational intensive. And then a couple of years ago, there was this paper by Rosas and colleagues, in which they found a more parsimonious expansion. Is not really an expansion of mutual information, is an extension of mutual information. So it's a quantity that up to order 3 is identical to the expansion of mutual information, then becomes something else. It's based on, we will see in a moment, on the ratio between total correlation and dual total correlation, which can also be extended to condition interaction, so an expansion of the transfer entropy. So the information basically is the difference between the total correlation, which speaks basically to redundancy, and the dual total correlation, which is a proxy for a synergy. And so the O information, as they called it, as the difference between these two, captures the net balance between redundancy and synergy. So in this sense, it quantifies whether a multiplet of variable is dominated by redundancy or dominated by synergy. And it has the advantage that scales nicely with a big number of variables. Still, there are some caveats that we will approach in a minute. So just as an example, if we compute these higher order multiplets in some local field potential data from a rat, we see here that you have different electrodes in different regions, and here you have the redundant multiplets at order 3, 4, 5, and 6, and they basically tend to cluster together electrodes from similar regions. On the other hand, the synergistic multiplets tend to include data recorded at different sites. We will see later on how to make sense of this measure. It was just an example of what these higher order multiplets look like. One important thing is that, for example, if you go from order 3 to order 4, from order 4 to order 5, etc., is that you need to make sure that multiplet of order 4 are not only there due to the fact that they contain multiplets of order 3 and so on. So every time you need to compute the confidence interval for the lower order and compare it with the confidence interval computed by Bootstrap of the higher order, and see whether you actually add new information going from order 3 to order 4 to order 5. Otherwise, the thing just explodes. Of course, when we have richer data, such as electrophysiology data, it's it's also convenient to seek for this expansion also in frequency domain. And so one way of doing so is by decomposing the frequency domain, the autoregressive vector autoregressive model of the multivariate time series, and using a state space representation and solving the Riccati equations. Basically, you find the spectral components, and from these components you can again find an expansion of the dual correlation and the total correlation, and find predominance of synergy or redundancy in the spectral domain. So this is a simulation study, and this is a study from a monkey in awake and propofol anesthesia study, in which we have 5 groups of regions, and we look at the all information in frequency domain in the 2 conditions, anesthesia and rest. And we see the difference across different bands. So this is the first line is the wide band, and then we have delta, theta, alpha, beta, and gamma. So this is an extension to richer dynamics, but this also works when you have no dynamics at all. So this is the case, for example, of a psychological network, so where you don't have time series at all. So, for example, you have different behavioral data collected across many subjects. And so one recent way of characterizing physiological conditions, psychophysiological conditions, is by looking at the interaction of different symptoms or different answers to behavioral questionnaires across multiple subjects, and have in this way a network-based view of these symptoms. And again, the idea is the idea of latent factors. So, for example, you cannot measure depression. You don't have appropriate measure for depression, but you can measure, for example, fatigue, insomnia, loss of interest, suicidal thoughts, etc. So this is what in psychometrics is called a latent factor analysis. So you measure these items knowing that they are expression of this factor that you cannot measure. And so, for example, this is a result of a study published a few years ago on network analysis of empathy items. So here you have different latent factors, which are, for example, empathic concern, perspective taking, etc. So, and here a network is a nice representation, but still you see that the latent factors are already grouped together. So already when you present the items to the subject, you know that these correspond to a construct, these correspond to another construct, and so on. So basically, here you have a network view, but is nothing surprising with respect to the division in 4 latent factors that you already have before asking the question to the subject. On the other hand, latent factor can be the mechanism, but again, if you look at the behavior, you can look at higher order interactions in the co-expression of this of these answers across several subjects, in this case almost 2000. And so we have some redundant hyperedges, which again, even if they look like crop circles, but you can see that they cluster together these variables. On the other hand, the synergistic hyperedges, that in this case only exist at order 3, contain contributions from different latent factors. By the way, passing this message to psychometricians is a huge pain in the ass. So this paper will stay on the archive forever, I guess. Anyway, another application is to artificial neural networks. So, for example, here we have a case of 3 layers of a neural network which performs recognition of digits. And so you have, for different multiplets up to order 16, 17, the presence of synergy and redundancy in the first layer, in the second layer, and in the third layer. So you see a modulation of the relative amount of synergy and redundancy when you increase the layers. And also, if you retrain the network with initial weights based on synergistic neuron, then you have less accuracy drops with respect to random or multiple information ANOVA or multiple information mixer strategy to rewire the network. So, so far we consider zero lagged interaction. We can also have an equivalent of the expansion of the transfer entropy by conditioning on the past of the time series. In this case, we have an example of again monkeys performing a decision-making task in which the neurons are divided in three classes, H, M, and L, depending on the mutual information between their activity and the actual action that the monkey performs. So there are some neurons which have high mutual information between their activity and the response, and others which less. In particular, the class L has zero mutual information with respect to the response. And so, if we look at this time the multiplets, but the multiplets of conditioned mutual information, so conditioned information, conditioning to the past of the time series, we have that the redundancy basically stays the same with different size of multiplets for the three classes. And again, the class L, the ones which are not informative with respect to the with the performing the actions, have always low redundancy, and the highest is for class H. On the other hand, the synergy shows an opposite behavior. So the synergy, which is highest for the most informative neurons at the beginning, when we increase the multiplet, goes down. On the other hand, when the increasing the multiplet size, the neurons which at order at pairwise mutual information were less informative, then they start becoming more informative. So if we consider time resolved measure, another way is local information. So in the same way that we have entropy, which is the integral of this quantity, you can have the local entropy, which is just the individual contribution at each point. So you can have the same for mutual information. And so in a simple application to a logistic map, and in the Granger causality, the local Granger causality, which is basically equivalent to the transfer entropy for Gaussian distributed variable, you see that you have some points in the space in which the local contribution of the driver to the target is even negative, so is misinformative with respect to the driver, and this is normal. So of course the net Granger causality will be non-zero and will be positive from x to y, because from y to x, because y is present in the generative model of x. So you will have a non-zero Granger causality between y and x, but there are some points in which locally the knowledge of y is even misinformative with respect to the future of x. And the same can be used for local information. So, for example, in the case of a frustrated system, you see that the ferromagnetic behavior is dominated by redundancy, while frustrated systems like this one are dominated by synergy. On the other hand, the configuration where the spins are not in agreement are dominated by synergy, despite of the sign of the coupling. So despite of whether the system is frustrated or not. So this is the local information. 0 is independent. Positive is synergistic, and this is redundant and negative is synergistic, and so you have that when you have discordancy of spins, you have a predominance of synergy. The same can be applied to music analysis. So, for example, here is an analysis of Bach chorales. I don't know if you can hear them. So yeah, I muted myself. Good. I think it is. Okay, now it is, right? Good. So in this case, we see that in time, we look at the information between the different chords and also the words. And so we see, for example, that there are some chords which are dominated by redundancy and some chords which are dominated by synergy. And also this changes when we also consider the relationship between the chords and the words. So of course, we have the Lord, the God, and Jesus, etc., which are the most represented variables. And indeed, there are some music theory figures, such as dissonances and alteration, inversions, and the fact of whether the chords or the words are root or non-root, so depending on their importance, we have a different amount of local synergy or local redundancy. So a relevant thing is that we have seen this before when we are looking at these figures, which basically looked like crop circles, is that it becomes a mess, honestly. And indeed, one of the successes of network science was to provide a compact view of a system. Then you say, okay, now we go for higher order interactions, and then I show you the network, and the network already is order 3, order 4, order 5, and it looks like a mess, even if it corresponds to reality. I mean, reality is a mess. It should not be, let's say, underrepresented just because we like a pairwise network better. Still, I see your point. That is a mess. And so basically the idea is to find some low order descriptors of these higher order dependencies. One way of doing so is, instead of focusing on the O information of groups of variables, we can focus on the change of the O information when individual variables or pairs of variables are added to the rest of the system to form the higher order multiplets. And so this basically means taking the derivative of the O information. So what is the variation of O information when a variable is added to the system? And then we have a variation of variations and so on. And so again, we can expand this to higher order, but of course, then we kind of defeat the purpose. So it's better to stop at the lower orders. Otherwise, it becomes a mess again. So the gradients are symmetric under permutation of indices, at least this. So we can, in this way, look at the contributions of individual variables to form higher order interactions, or the contribution of pairs of variables in forming higher order interactions. And again, example of our favorite system, that is the ISING spins. So for example, here, spin 1 is the only one which can participate in synergistic multiplets, and indeed, as the temperature changes, the first order gradients is synergistic only for spin 1. On the other hand, for spin 7, it becomes more redundant. Here we have another system of spins connected in this way. And so this is the curve of susceptibility, and you have the first order gradients, and then you have the second order gradients, third order gradients, and the local O information for all the groups of variables. And so again, for example, here we have that the second order gradients, which contain spin 1, again, are synergistic, and the other ones are redundant. So here we can see, let's say, pinpoint the contribution of individual variables to higher order interactions. This is applied to fMRI data where the individual nodes are the intrinsic connectivity networks. So these are the first order network, and the default mode network is the only one which has some redundancy. All the other one are has some synergy, or the other one are basically all redundant. And it makes sense because basically fMRI is made by redundant activity. You have the blood flow, respiration, apart from the very close sampling, which all speaks to redundancy. Then, of course, if you go to second order and third order gradients, you have a more expression of synergy across different combination of the different intrinsic connectivity networks. And if we go back to our first example of local field potential data, here is the first order gradients. So it's all redundant except from the hippocampus. And then this is the second order gradient. So groups of variables coming from different brain regions, which contributes to synergistic or redundant interactions. So this so far was net presence of synergy redundancy. What if we want to have synergy redundancy together? We can use the partial information decomposition. Partial information decomposition needs to twist the arm of Shannon because Shannon theory cannot accommodate a fourth relationship, which would allow to have synergy redundancy as two non-negative quantities. And so one possible choice, even if not the only one, is to define redundancy as the minimum of the two individual transfer entropy. This is a convenient choice because the redundant transfer entropy is independent of the fact that the two source processes are correlated, possibly for the influence of a third external variable. And so this is particularly convenient to in two cases. The first one is to look at information dynamic at transitions. So we know that when a system is completely disordered, you don't have synchronization and you don't have information transfer. On the other hand, when a system is completely synchronized, the information transfer also drops because we don't need anymore the driver to predict the target, since all the components of the system basically do the same. And so this is a case of explosive synchronization of Kuramoto oscillators, and indeed the total transfer entropy peaks at in the same regime as the synchronization. Again, the ISING model is an example of displaying this transition, which in lattices is a sharp transition, but of course is a paradigm of other types of transition to the order, like polarization, stock market crisis, epilepsy, but also non-negative stuff like learning a new pattern, etc. And so a few years ago, it was shown that the pairwise and the global mutual information, they peak exactly at the critical temperature. If we ask what comes before, the transition to the order or the peak information. So in a paper of 10 years ago now, Barnett, Seth, and colleagues showed that the pairwise transfer entropy has a peak exactly at the transition. On the other hand, the global transfer entropy has a peak in the paramagnetic phase. So in this sense, the global transfer entropy can be seen as a precursor of a transition. On the other hand, here we need dynamical data. Can we have a precursor also on static data? And also, do we really have to measure all the variables, or we can build precursors based on a small number of variables? So if we look at partial information decomposition, we see that is the synergy that peaks in the paramagnetic phase. So here it's inverse because beta is the inverse temperature. That's why the peak is on the left, while here it was on the right because it's the temperature. So synergy peaks in paramagnetic phase, both in the instantaneous and in the lagged case. And also the synergy peaks approach the critical values as the amount of synergy decreases. So for example, if the target is spin 1, spin 2 and 3 are very synergistic with respect to 1 because they are on opposite sides. So the peak is farther away than the critical transition. On the other hand, spin 3 and 6 are less synergistic and more redundant. And so the peak moves towards the critical transition. So the synergy can be seen as a precursor of this transition. And again, this is an example of higher order behavior from links whose mechanism is pairwise. And so we have a static or lagged version of the partial information decomposition. When is partial information decomposition especially relevant? When we have signals that are apparently very similar to each other. So for example, if the drivers are some depth electrodes where we know that the focus of epilepsy is, and the target is the cortical grid on the surface of the brain, if we look at interaction information decomposition, we see a difference between preictal and ictal phase, but we don't see any difference between the two putative sources of ictal activity, which are electrode 11 and 12 depth in the hippocampus. On the other hand, if we look at the partial information decomposition, we see that there is a change of the unique transfer entropy from electrode 12 in the preictal and ictal phase, which is not present in the electrode 11. And so this is also true at different time scales and for different seizures of the same subjects. So this is a case in which partial information decomposition is more useful than interaction information decomposition to disambiguate the role of this two electrodes. Another case is global signal regression in fMRI. So we know that this is a functional connectivity matrix, or the equivalent with mutual information. If you perform a global signal regression, you know that you introduce artificially negative links. Why? Because since the global signal is a signal present in all these rows, but the global signal reaches different regions at different time points and is expressed differently in different regions, if you substitute it, basically you introduce a collider. So it's conditioning on a collider, and so you have some negative correlations. And this you see in here. And you also see that the global signal is very similar to the signal, the Bolt signal in the vessels. So on 1,000 subjects, the median correlation is more than 0.9 between the global signal and the Bolt signal in the vessels. That's why people want to get rid of non-neuronal signal by regressing the global signal. On the other hand, if we look at the joint role of global signal and the Bolt signals in the vessels, we can basically avoid of throwing the baby with the bathwater, basically by understanding what is the contribution of the global signal and which is the contribution of the signal in the vessels. And so in this case, if we look at the unique information between global signal and different brain regions divided in network: visual, somatomotor, dorsal attention, visual attention, limbic, frontoparietal, default, and then subcortical and cerebellum. This is the unique information of the global signal to the brain, the unique information of the vessel broad signals to the brain, the redundancy, and the synergy. So you see, and these are different time scales. And so you see that there is a differential contribution of these two sources of noise, if you want, the global signal and the signal in the vessels. And if, as a control, we took at we took the calcium signal in the vessels measured in a rat, you see that there is no unique information from the vessels with the calcium measures. On the other hand, there is when we consider hemodynamic Bolt signal. So is the nature of the Bolt signal, which is literally made by blood flow, respiration, and heartbeat, which introduces some non-negative information towards the different brain regions. So as a final application, we look at spins on the structural connectome. So if we implement a system of spins on the structural architecture of the human brain, we observe that at the critical point, the correlation between spins is maximized, and also the transfer entropy between spins is maximized. On the other hand, the correlation between the transfer entropy or the correlation between the spin correlation and the structural connectivity is minimized. So it means that when the dynamical repertoire is richer, so at the critical regime, somehow we need to forget the underlying structural connectome, which makes sense if we want to have the coexistence of different functional patterns on top of the same structural pattern. And so knowing that the synergy is a particularly relevant quantity in joint information, we implemented different the same ISING model on different connectomes and look whether there is some association with age, and we saw that the synergy is correlated with the strength and the between the centrality and the closeness, even though in a nonlinear way. And there are some hubs in the brain which are correlated with which expresses mostly the synergy. And indeed, there are some areas which are correlated with age and some areas which are anti-correlated with age. And in some areas, this correlation is limited to the first 30 years of age, and then they subside, and for others, you have a more constant trend. So to take home, synergy and redundancy are a natural paradigm to study emergence and to encompass both segregation and integration, where redundancy speaks to the degeneracy and synergy speaks to cooperation of degrees of freedom. Some concepts that we observe in neuroscience, such as dimensionality reduction, manifolds, Markov chains, data processing inequality, can all be seen under the lens of joint informational content. Then synergy is the informational quantity which mostly acts as a precursor of transition. And so this framework can also be seen in the framework of network neuroscience and graph theory in general to build functional hypergraphs of different orders. Thanks.
Thank you very much, Daniele. That was quite a tour de force, from spins to spikes to behavior.
Sorry,